So today we're going to work on electrostatics. A few numbers that we need to know. The first one is the charge of an element. An element has a charge of 1.6 times 10 to the power of minus 19 coulombs. So the negative is just there because we know that electrons are negatively charged. We're going to be working with Coulomb's law, and it has a constant. The constant is 9 times 10 to the power of n. Now, when it comes to electric charge, because electric charge is so small, we will always represent it with regards to either millicoulombs, microcoulombs, nanocoulombs. So the milli is times 10 to the power minus 3. The micro is times 10 to the power minus 6, and the nano is times 10 to the power of minus 19. When we represent charge in terms of our calculation, if we write a big Q, it means that it is going to be the object that creates or produces the electrical field, whereas if we write it with a small q, it's going to be then the object that's going to experience or feel the electrical field. Okay, so in electrostatics, we're going to work with the conservation of charge. The conservation of charge says charge cannot be created or destroyed, but are separated and transferred from one object to the other. This then implies that the net charge of an isolated system must then remain constant. Okay, so this is just going over things that do have charge. No need for us to worry about ourselves about that. The only thing we need to understand is that like charges are going to repel. So a positive and a positive is going to repel, or a negative and a negative is going to repel, whereas a positive and a negative is going to attract. So unlike charges are going to attract. One last thing here is that if we have a charged object and we move it close to a neutralized object, then it's going to polarize that specific object. What do we mean by that? So a neutral atom or a neutral object is going to be one that has equal amount of a positive charge and equal amount of negative charge. They must be evenly spread out. Now, let's say that this object here is positively charged. So it has more positive charges, in this case protons, than it does have electrons. When we bring it close to this object over here, the protons and electrons, or the positive charge and the negative charge, are going to rearrange themselves such that the negative will only be found in this side and the positive will only be found in that side. And we would say that our object is now being polarized, where we can clearly see a partially positive side and a partially negative side. Okay, so now we're going to look into the conservation of charge. So we have two objects here. We have object A and object B. Object A has a charge of 12 microcoulombs, and object B has a charge of minus 6 microcoulombs. The thing about charge is only electrons are allowed to move. Now, if we look at object B, we will see that it has an excess of electrons. That is why it is negatively charged. So what's going to happen is that the electrons are going to move to A until object A and object B have the same charge. From there on, they will separate from each other. The question wants us to calculate the new charge on object A after A and B come into contact, and then after they come into contact, they must separate once the charges are equal to each other, because we said like charges are going to repel. So before we get into that, let's get into how do we then calculate the new charge that's going to be found on object A and object B. So we're going to say the charge of A plus the charge of B divided by 2, and we will see that overall the new charge would be 3 microcoulombs. If we want to see what was the change in charge, we will say the new charge of either A or B, because it will be the same, minus the old charge. Now, the old charge we're going to use here is the sphere that gained the electron. So if we look at our object, we said that there will be a transfer from sphere B, to sphere A. So that means that we would use 12 here, and we would see that the change is minus 9 microcoulombs. What does that mean? It implies that we initially started with 12 microcoulombs for object A, and it transferred 9 microcoulombs. It received 9 microcoulombs, and its final charge was 3 microcoulombs. Whereas B transferred its electrons to A, it lost 9 microcoulombs, and its final charge is going to be then 3 microcoulombs. Once we know that we have transferred a charge of minus 9, we want to know how many electrons have been transferred through this interaction. So we're going to say the change in the transfer, or just the transferred electrons, divided by the charge of 1 electron. So since the transfer is a negative 9 times 10 to the power of minus 6, and we know that 1 electron has a charge of minus 1.6 times 10 to the power of minus 19, we would then get the number of moles as 5.63 times 10 to the power of 13. So we have another question here. It says, calculate the number of electrons that will be transferred from A to B if they came into contact with one another. So object A has a charge of minus 20 microcoulombs, and object B is minus 4 microcoulombs. We can see that A has an excess amount of electrons, so we're going to transfer electrons from A to B until these two have the same charge. The first thing we want to calculate is what would be the new charge of object A on object object A and object B after they meet. So we will have here QA plus QB here divided by 12. So after the transfer from QA to QB, we would have an overall charge of minus 12 microcoulombs on both of the electrons. Now, to calculate the change, we know that the U is minus 12 microcoulombs, and we know that the one that got the electrons was the minus 4. So that's the one we're using. It's the one that gained the electrons. The minus 4, and we'll say that the change here was a minus 8 microcoulombs, and then we can calculate the number of electrons that were transferred by dividing that change over there with minus 1.6 times 10 to the power of minus 19. So we have another example here. It says when sphere A came into contact with sphere B, 10 times 10 to the power of 10 electrons were transferred from B to A. They want us to calculate the original charge on B if after contact both A and B charges are equal to 4 nanocoulombs. So the first thing we want to do is calculate the change in charge, because we know the number of electrons that were transferred. We know the charge of an electron. Therefore, we would say that the change in electrons was minus 1.6 times 10 to the power of minus 9, or nanocoulombs. Now that we have the change, we can use this equation that says that the change is equal to the Q new minus the Q old, but the Q old must be the one that got the transfer, right? So the one that got the transfer here, according to our question, was A, not B, but we are looking for A. Just to make sure, it says we're transferred from B to A. We understand that A is the one that gained the electrons. So the charge that we are calculating here belongs to A and not B. To calculate B, we would use this equation here that says the Q nu, which they gave to us, is equals to the QA, which we calculated. We do not know what QB is, over 2. And if we simplify it, we will get to a point where we calculate QB, and QB was a charge of 2.4 nanocoulombs. And yes, it has more electrons than the 5.6. It's less positive than the 5.6, therefore it has more electrons than the 5.6. Okay, then now we're moving on to Coulomb's law. That tells us that the electrostatic force between 2 point charges is directly proportional to the product of the charges and inversely proportional to the squared distance between them. So here we have our equation that says F is equals to K. We talked about K, but you also find it in your formula sheet, is equal to Q1 multiplied by Q2 over R squared. So it exactly says that equation is the same as the rule. So we have question and example here that wants us to calculate the magnitude of the electrostatic force between A and B. A has a charge of 16 microcoulombs. B has a charge of minus 8 microcoulombs. So then, and then there's a distance of 50 centimeters between them. We would just use our equation where we substitute in. When you substitute in, you do not necessarily have to, you don't actually, let's just put it this way. You do not have to take into consideration the sign. We only take into consideration the sign when we look at what type of attraction, what type of force they would feel. Now, B is negative and A is positive. And we understand that unlike charges are going to attract each other. So here we're going to have force of attraction. As you can see, A is attracted to B with a force of 4.61 newtons, and B is attracted to A with a force of equal. So they are equal, but just in opposite direction. Question 2 wants us to calculate the distance between A and B if the magnitude of the electrostatic force between them is equal to 10.80 newtons, and they both have a charge of 2 microcoulombs. We just use our equation. We just need to rewrite it so that R is the subject of formula, and we will substitute in our values and calculate. So in meters, it's going to be 0.057735 meters. But if they ask you to report it in centimeters or micrometers, be willing or be able to do that. Right. Here we have 3 charges. We have sphere A, object B, and object C. Object A has a charge of 2 microcoulombs. Object B has a charge of 3 microcoulombs, and object C has a charge of minus 14 microcoulombs. We can see that the distance between A and B is 20 centimeters, and the distance between B and C is 80 centimeters. We are asked to calculate the net force that B is going to experience because of object A and because of object B. So the first one we are calculating is the force that object B is going to feel due to A, and we get a 1.35 Newton. Now, object A is positive and object B is also positive, implying that there will be a repulsion between object A and object B. They should move away from each other. So the force that B is going to experience because of A is going to be 1.35, but it's also going to be repulsion, so it will go to your right. And we can see the value there and the force being represented by an arrow. We also calculate the force between B and C, or the force on B because of C. We get a value of 0.59. Now, B is positive and C is negative, meaning that B is going to be attracted towards C. So The force of C on B is also going to the left and giving us a final value of 0.59 newtons. And for us then to get the resultant, because now they're going in the same direction, all we would have to do is add them. We get a resultant force of 1.9 on B to the right because of A and C. Then we have here, they want us to calculate the net force experienced by QB because of QA and QC. If we look at QA, it has a value of minus 8 microcoulombs. If we look at object B, it has a force of 4 microcoulombs. And if we look at object C, it has a force of 16 microcoulombs. So we have to calculate the force that B will experience because of A. We can see that B is positive and A is negative, implying that B is going to be attracted to A. So the force must go up. And here we see that QB is positive and QC is also positive, so there will be repulsion pushing QB to the left. So we will calculate the force that B is going to experience because of A using our Coulomb's law. And we will also calculate the force that B feels because of C using our Coulomb's law. Here are the equations. We can see that B will experience a force of 1.15 newtons going up, and because of A, and it will experience a force of 0.4 newtons to the left because of C. To calculate the resultant force, we're going to use Pythagoras theorem because this is a triangle. So basically what they did is they took FAB, they moved it here so that we can close the gap and see where our resultant force is going to be by using the tail head method. And we can use Pythagoras theorem to calculate a resultant force of 1.2 newtons. If we were asked to calculate the direction, we would have to just calculate that angle there, and that's just going to use 10, and we'll get an angle of 70.8 degrees. Right. Questions?
No questions.
Here they're talking about bearing. So bearing is when you take into consideration from the positive y-axis all the way to where your resultant force is. So you would have to say 270 plus that 70.82 to get the bearing, and the bearing would then be 340.82 degrees. Bearing is better as a direction because they cannot misunderstand you. Getting that angle is a little bit could be misread or misunderstood. So if ever given the chance, choose bearing over anything else.